Hello and welcome to this video. In this video we're going to be looking at the topic of internal resistance. So in all of these videos so far, whenever we've mentioned any electrical components, we've always considered them to be ideal. And what we mean by ideal is that they satisfy the perfect prediction conditions. Meaning, for example, if we were to look at a ohmic resistor, its perfect condition is that the resistance never changes. Okay, let's say we were to look at the idea of an ammeter. So this is something we would consider. We would have to have an ideal ammeter. So an ammeter has to have zero resistance. Okay. A voltmeter would have to have infinite resistance. Okay, and a battery or a cell would have to have zero resistance. Okay, now in practice this is very, very difficult and some would say impossible to obtain. Okay, the true reason behind this is because an ammeter is not a superconductor. If we make superconducting ammeters, then we will be able to get perfect ammeters. But other than that, we can reach very, 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 very small resistances, but not exactly zero. The same for voltmeters. We can't reach infinite resistance because that is impossible. But we can have very, 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 very high resistances for voltmeters. And for batteries, ideally, we want the resistance to be as small as possible. Which is true for most batteries, but in some cases we'll get we'll have some internal resistance of a battery, and that's what this topic is going to talk about. So let's look at what we actually mean by the internal resistance. Okay, so the battery itself, when we draw it out having some internal resistance, will look something like this. Okay, this is the symbol that we give to a battery with some internal resistance. Now, the way this depicts it is saying that we have the battery, and inside the battery we have some resistance that we call little r. Now, this isn't true. It's obviously, we don't have a tiny resistor inside the battery. What we're doing here is we're modeling the resistance of the battery to be its own resistor, because this basically helps us to separate what's charging and what's discharging, and so that way we get a more conclusive way to do the calculations with these. Okay, so what we would say is that with this battery, then what's happening is, let's say we had an electron that's coming in this way, and the electron comes in, it gets charged up here, so the electron currently has the EMF amount of volts, and then it immediately discharges through here at some amount and then goes out. Okay, what we would call that is the terminal PD. Okay, so the terminal PD we would say is the we would call it the maximum potential across the terminals of the battery, but it's only when a current flows. When a current is flowing. Okay, if we didn't have a current flowing through the battery, then we don't have any electrons moving, and therefore we have no collisions, and therefore we don't have any resistance. Okay, so what we do usually is I'm just going to model this as, let's say we have just some resistor here, and let's put a switch into this. Actually, let's put a switch here, and let's put an ammeter on the other side. We'll put an ammeter in here, remembering from GCSE, ammeters always have to be in series with the component, and I'm going to put a voltmeter across the battery. Okay, knowing voltmeters always have to be in parallel with the components. So this circuit is a series circuit with a voltmeter attached to the battery in parallel, and the switch S is open. What is the voltmeter going to read? So when S is open, there is no current. So what the voltmeter reads is actually the EMF. So voltmeter reads the EMF of the battery. Okay, so this is the maximum possible work done per unit charge that we can have going to a single electron if the resistance is 0. However, if we then close switch S, so when S is closed, it means we will have a current flowing. There is a current. And therefore, what we're going to measure the maximum of when we have a current flowing is going to be called the terminal PD. So voltmeter reads what we're going to call V is the terminal PD. Okay. Now this whole setup will be a required practical. Okay, so it will be something that you will have to measure. Measuring the internal resistance of a battery is something you will have to do. But what we're going to do now is see, using the ideas that we already know, using our 3 fundamental laws of electricity, Kirchhoff's laws and Ohm's law, let's see if we can actually come up with some sort of expression that we can use to calculate what the internal resistance of something is. So what we can say is, we know everything we've been talking about is to do with a voltmeter, so we're always looking at the potential, okay, which means we're going to be looking at Kirchhoff's voltage law. Okay, so Kirchhoff's voltage law, if you remember back, states that the sum of all of the EMFs in a loop must be equal to the sum of all the potential lost in any loop. Okay, in this case we only have one loop going around. We can have this voltmeter, but it doesn't really count as anything. So let's just analyze this loop. So our total EMFs coming in is the EMF, and our total things coming out is going to be the potential across here, which is going to be equal to the terminal potential, because that's when a current is flowing. The maximum we can get out here is going to be big V. So this has a potential big V, and then let's say this has a potential across it. Let's just call it V subscript R. So this big V is the potential across the actual resistor. Now, it doesn't always have to be just a fixed resistor. This could be a whole circuit, but R would just be the total resistance of the circuit, plus the internal potential that we lose across that internal resistor. Now, there is something in common with both of these, and that is the fact that V is equal to IR. So both of these potentials we could describe as being the current passing through them multiplied by the resistances. And we know the current passing through them because this is a series circuit from Kirchhoff's current law. We could say the current is the same everywhere. So they both have the same current, and we've been told what the symbol for their resistance is. So this becomes EMF is equal to the current times this large resistance plus the current times the little resistance. We can factorize that and say that EMF is the current multiplied by the sum of all of the resistance of the circuit. Okay. Now, this expression, whenever you hear the term internal resistance, is definitely the thing that you want to look at. It'll be the first thing I wrote down. It's the only equation in it that actually includes internal resistance. So this is probably going to be your first tool to go to if you ever get a question that says that you have some internal resistance. Some questions will say that you have negligible internal resistance. In that case, you don't have to worry about this equation. Okay. Now, what we can form from this practical, and what we'll go over again in the required practical video, is a graph. Now, this graph is saying we're going to basically choose the values of R that we have, or we can have a variable EMF source. really depends on how your school is setting up the practical. I would say it's usually going to be a variable EMF source. And what you're going to do is close the switch and measure different values for the current and the potential. You should measure at least 6 values to get a good enough graph. And what your graph is going to look like is that, let's do a VI graph. I'm not going into the negatives in this case because I know that it has to be a positive. So when my current is 0, I have my maximum potential on this voltmeter, and that is going to be the EMF. Okay. As I slowly increase the current, I know the terminal PD is going to decrease. Now, the terminal PD decreases because if I increase the amount of current traveling through this resistor, since V is equal to I times little r, if I increase the current, I'm increasing the potential here, which means the total potential that we get given out by the battery is going to decrease. Okay, so you can think about this as a charging and discharging station. So we might charge it up, the EMF might be like 15 volts, but then the potential across here might be 5 volts. So our terminal PD, let's say VT, so V for terminal, would just be 10 volts. Okay, so it charges up 15 volts, discharges 5 volts, and we get a terminal PD out. The more we increase the current traveling around here, the more potential is going to be lost. So in general, as I increase the current, my potential is going to decrease. Okay, and what this means is that the gradient of this, since this is a VI graph, should be the resistance, but what we're going to find is because this is actually going to be a negative gradient, the gradient is going to be negative the internal resistance. Okay, so you can always work out what the internal resistance is by plotting a graph of V against I, and then the gradient of that graph is negative the internal resistance. Okay, so these questions tend to be tricky for people purely because of this idea of the terminal PD being different to the EMF. I would say in your head, whenever you're tackling any electrical circuit, always try to follow the path of an electron and see what it has to go down, if it has to collide through that thing, and so on. Okay, just try and map it out to see what the path the electron has to take, and i.e. how many electrons are going to take that, so you can look what the current is going to be at each point, and then also look at how much energy does the electron have at that point, and that's going to allow you to look at the potentials throughout any circuit. Hopefully all of this internal resistance stuff makes sense. Thank you for watching.